Okay, so welcome back and welcome to this module on the Aluminate hydrates. In the last slides, we saw about the hydrates that form from the hydration of the calcium silicate phases. That's to say C3S mainly and C2S later on. And in this module, we're going to look at the hydrates that form from the aluminate, that's to say the C3A phase, and the ferrite phase, usually called C4AF. These phases are not as prevalent as the ones from the calcium silicate phases, but nevertheless quite significant. So in this slide, we see the phases that are formed from a typical ordinary Portland cement. And while the phases from the calcium silicates, that's to say calcium hydroxide and CSH, are making up about 65% of the volume of the final paste, the hydrates coming from the C3A and C4AF, that's to say this AFM and AFT, are still accounting for about 25% by volume. So this is a quite significant amount of the final volume of the paste. Now, these aluminate hydrates broadly come in three families. First, we have these rods, which are called ettringite. Now, the formula of ettringite is as written here. That's to say, for each molecule of C3A, we have 3 molecules of calcium sulfate and then a lot of water. And in what we're going to see in a lot of these hydrates, we can have a replacement of the aluminium ions by iron ions. These are very similar elements from a chemical point of view. And because of that, as well as the term ettringite, which means the form with aluminium, we also have this term AFT. So A and F means the possibility for having either alumina or iron oxide. And T is the other anions, that's to say in this case the calcium sulfate. And here we have 3 calcium sulfates, so 3 gives us the word tri. Now the second family has many more variants depending on the different anions that we find. And for this reason, we tend to use more often the generic word AFM, standing for aluminate ferrite monophase. And finally, we don't usually have very much of it in common cement paste. We have the hydrogonase. And in the next slides, we're going to look at each of these families in turn and see in more detail about their crystal structure and the possibilities of solid solution. Ettringite was first found in the town of Ettringen, hence the name. And in nature, it can form these very big crystals. So if we look at this picture here, we can see we can get these really huge crystals which have this hexagonal cross-section. Then we can see the crystal structure is like this. So we have columns, and in these columns we have the alumina and we have the calcium surrounded by lots of hydroxide ions. And then in between the columns we have these the sulfate molecules. More generally, the formula is like this. So we have 3 calciums, either aluminium or iron, and then these hydroxide groups and the water molecules. And then the X3, this can be a divalent anion. In this case, we're talking about here, it's sulfate, but another possibility is carbonate. So ettringite forms early on in cement paste, and some may later transform into the AFM phases that we're going to see later, depending on the amount of sulfate and carbonate we have in the paste. So, in most cement paste, and indeed most blended cements, there's not much variation, in fact, in the composition. The composition we find is pretty close to the stoichiometric ettringite. So even though we know we can have this solid solubility between aluminium and iron, in actual cement paste, because of the high alkalinity of the pore solution, not much of the iron actually goes into this ettringite phase. It's pretty much just the pure aluminum form. We have some solid solution, as I've mentioned, between carbonate anion and sulfate, and this can be stabilized at low temperatures. So at low temperatures, we tend to get more carbonate going into the AFT phase. And the other important aspects about ettringite are it has this high water content, as we've seen, and because of this, it actually has quite a low density. Okay, and because it has low density, this means it fills up a lot of space. So in terms of filling space, it makes a very positive contribution to strength development and other properties. Now, in terms of stability, the stability of ettringite thermal terms is very, very similar to that of CSH. Here we see the thermal decomposition curves by DTA for ettringite and CSH, and we can see that the peak for the two is in a very, very similar position at 120, 140, around that kind of temperature. Now, as we move to the second group, AFM phases, these are part of a much larger group of hydrates called layered double hydroxides. Some of you may have heard of layered double hydroxides because they're really researched quite a lot nowadays for their interesting electronic properties. And in these layered double hydroxides, we have layers of M2 and M3 ions. And then between the layers, we have these anions. And the fact you can put in a lot of different anions leads to what's called polytypism. So in this larger family of layered double hydroxides, quite a large number of groups have been defined. In fact, 8 groups with this what's called hydrotalcite in the supergroup. So this hydrotalcite where you have 3-to-1 divalent to trivalent ions, the quinite group where we have 2-to-1 divalent to trivalent, so on. And finally, we come to the hydrocalamite group, which is what interests us, where these divalent ions are calcium and the trivalent ions are aluminium. And they exist in the ratio of 2-to-1. So this is the AFM phases. This is the kind of layer we have in those AFM phases. It's a distorted layer similar to what we have in brucite with 2 calciums to 1 aluminium. And then the anion that can go in between that gives us the AFM phases, most commonly, the first one that gave its name to this group are the monosulfates, where the anion is sulfate. But probably, in fact, more common today is where we have carbonate ions, as in monocarbonate. And we can also have hydroxide ions, as is hydrocalamite. We can have chloride ions, as in Friedel salt, and even complex aluminosilicate ions, as in strecklingite, as we will see. Now, one of the key questions in understanding these phases, and particularly how much of the forms and what is their contribution to space filling, we need to know what is the extent of solid solution. So if we take the 3 most common, or if we take the most common substitution, which is between sulfate and carbonate, we have these 3 phases. We have monosulfate we see at the top, we have the monocarbonate we see at the bottom on the right, and the hemicarbonate which we see at the bottom on the left. Now, because of the different anions in the interlayer, you can see that the interlayer spacing for these crystal phases is quite different. 8.9 for the monosulfate, 7.8 for the monocarbonate, and 8.2 for the hemicarbonate. So these may not seem that big, but they are big enough such that in fact we find that these differences mean that we get really no solid solution between these different phases. And the transformation from one to another really occurs by a dissolution and reprecipitation of the new phases. And if we look more broadly, also including the hydroxide phases, the hydrocalamite phase down here, this shows us that really the only regions of solid solution we have are on this axis between the hydrocalamite and the sulfate form, where we can have some solid solution. Otherwise, there's really very little solid solution. As I said, classically, when people are thinking about cement hydration, they think about ettringite forming, and then most of the textbooks say, yes, there is monosulfate forming. And this is what we can see happens in a cement without limestone. Here you can see that at 1 day and 7 days, ettringite is dominating, but by the time we get to 1 year, we clearly have a lot of monosulfate phases. Now, most cements made today do in fact contain a small amount of limestone. 3 or 4% is typical, because this amount of limestone has been shown to improve properties and at the same time gives us a slight reduction in the net CO2 emissions. And when we have those cements with limestone, then we can see the picture changes quite dramatically. And instead of the monosulfate phase here, we have instead forming, first of all, hemicarbonate at for about 7 days, and later on monocarbonate. And this is what is one reason why we get improved performance with this small amount of limestone, because small amounts of limestone can react with the calcium aluminate from the cement, forming these extra phases, and this means we have more space filling and more strength. Okay, so finally in this AFM group, we're just going to have a quick look at this phase called stratlingite. And this phase called stratlingite has this very complex aluminosilicate groups in the interlayer. You can see now that this has increased quite dramatically the spacing of these interlayers, from about 7 or 8 we had in the monosulfate monocarbonate cases to this value of 12.6. And this can be quite an important phase where we have very high contents of alumina and silica reacting in blended cements. And thermodynamically, it only forms once all the portlandite's been consumed. But in reality, we can often find stratlingite where we still have small amounts of portlandite present. So finally, in this module, we're going to look at the hydrogarnets, and the classic formula for hydrogarnet is this formula C3AH6, which is also known as the mineral catoite. And more generically, what we see, again, we can have solid solution between alumina and iron, but now we can have a solid solution between 1 silicate group and 2 water groups. So this is why they're called hydrogarnets, because if all the water was replaced by silicate, this would be the garnet structure, and in reality we always have quite a bit of water. And in this case, this is actually the phase where most of the iron goes to in Portland cement paste. So I said that the iron, because of its low mobility in high alkali solutions, didn't go much into the ettringite, doesn't go much into the AFM phase, but it does form these silicious hydrogarnets, which there ends up being quite a lot of, but it's rather poorly crystalline, so not often well detected by XRD. Now, other important aspect about this phase is it's got a low water content, and because it's got a low water content, it has a high density, and this means that it's less space filling. So if we had a lot of hydrogarnet, as we would get if we cured it at a high temperature, this also contributes to the relatively poorer strength at high temperatures, because this phase occupies less space. So here are some other pictures of the crystal structures of the hydrogarnet. We have it's a sort of 3-dimensional structure in which four-fold coordinated silicon connects the 6 coordinated aluminium. It's predicted to form quite a lot in blended cement, but as I said, really not much except for the iron. So if we summarize this module, what we've seen in this module is that the aluminate containing hydrates are a very important part of the hydrate phase assemblage. They make up typically about 25% of the volume in mature paste. They do contribute to space filling, and therefore they contribute to strength development very much in the same way as CSH. In paste, as long as we have a continuous CSH phase with ettringite and monosulfate finely buried in it, then they are contributing in the same way to strength development. Ettringite can be formed with different substitutes, but in most Portland cement paste, most blended cement paste, it's really very close to the stoichiometric formula. In AFM phases, on the other hand, solid solution is much more important, and limestone, as we find, almost ubiquitously present in modern cements, favours the formation of carboaluminates rather than monosulfate phases, as you've probably learnt in the past. Vinyl type hydrogarnet forms only at long ages or at high temperatures. Okay, so thank you very much.